How is the homework going?
It's so long.
Okay.
So long, yes.
It's very long.
The last two problems were interesting.
Interesting.
Especially the last one specifically is, I think,
The delta function problem?
yeah, probably I wouldn't say the trickiest. There's an easy way to do it and a hard way to do it.
Yeah.
Figure that out after.
Yeah, it's long. And there is another homework due Monday.
Monday, okay. The one also very long?
No, that's shorter because you have living. But you have only very little time to study.
Yeah.
So in that sense, it's long. Rocky, you want to say something?
No.
No, go ahead. Seems like you want to say, but then you're.
Feel agree.
Feel free, right?
Plus 1 day if you want. Oh, that'll be great. Okay, so yeah, go ahead. So 1 or 2 days, let's say, but not more than.
Okay.
Is homework too much? Do you want me to reduce it?
This one is a little bit lengthy, it's not better, it's a little bit time.
If I reduce the homework, you get less practice also. Exams will be
Oh, yeah.
new for you. So,
That's okay.
so it seems to me it's okay. So, but if you really say that no, homeworks are very long, then I can't.
Just from my experience with
Last time?
classical mechanics,
Uh-huh.
this homework specifically was kind of uncharacteristically long, only because of how much we had to practice on it. So I think the next homeworks should be not too bad.
So it's okay, you're saying.
Yeah.
I think, yes, and anyone that's concerned should have a little bit of ease for the upcoming homeworks.
Right.
This
Usually
one
it is
long.
this long, yeah. But then you had 10 days. There was a Labor Day in between. But probably all of you started 2 days back.
Labor Day is Labor Day.
Oh, I see. So I see the joke. Okay. So we already talked about vectors in this course. We have been talking about vector components, basis vectors, and so on. But most of the time we have been sticking to rectangular coordinates. But in general, how do we develop a basis set? That's what we want to discuss today. Like starting from the scratch, just the idea of a vector. How do you build a concept of a basis associated with a vector? So just so that we can have nice diagrams, easier to represent, I'll be mostly trying 2 dimensions, but there is no restriction like that, especially 3 dimension spherical coordinates are very standard. So you should be able to do this for whatever I do today here for cylindrical coordinates. You should be able to at least do it for spherical on your own, right? That's the expectation. So how do we proceed? Let's say this is vector space in general. This is the idea that you will be seeing in quantum mechanics very much, where you have a basis vectors which play a very important role. And this is also called curvilinear coordinates. And this also plays a very important role if you're trying to do anything in general relativity. So there coordinates become very important. So what are coordinates? So let's begin with what exactly is a coordinate. Coordinate is a set of points that you uniquely use to find your position, let us say. That doesn't have to be position. So a set of points that specifies your position clearly. On the surface of a sphere, it is a latitude and longitude. Right? What is our, I like to ask typically, what is our latitude in Carbondale?
37.7.
It's on your rocket?
Yeah.
That's good. Is it a digital one or is it mechanically written?
It's engraved.
It's engraved. Okay, nice. Yeah, I always thought it was 39 or so, but Kane says it is 37 points, so 38.
In our first semester, we did that one as a quiz.
Yeah, the quiz.
So it was how much?
37 points.
37 point. Okay,
Yeah, he is right.
so that's the angle our place makes with the equator, right? North pole will be 90 degrees, equator is 0 degrees. Anywhere in the southern hemisphere is negative, so that's your latitude. And longitude is, you pick 0 if that longitude is passing through England. Otherwise, on the east coast it will be positive angles. On the left, on the west coast it will be negative. Overall, there are 360 degrees. So that's one way of looking at it. So you have to coordinatize, and how do we do that? Let's say think of a plane. One way of coordinatizing is you use a set of lines. These are not lines really in 3 dimensions. These are surfaces. So these are a mesh of 2 set of surfaces uniquely coordinatizes your point. So that's a coordinate, right? How would you do this? This is y at this point. This is x is equal to constant. Correct? Let's say x equal to 0. So the moment you say x is equal to 0, there is a surface, not really a line. It's a surface, and here this is y equal to y naught. So, and that is of course z equal to z naught also. So how many surfaces do you need for specifying your point on a plane? Oh, sorry, in 3 dimensions it is 3, and these are planes in our. So that is 3 planes. And these are family of planes. As you move the plane with one parameter alone changing, then you get independent surfaces. Is that clear? Now, if you want to do the same thing for cylindrical coordinates, we want to do a unique way of mapping, coordinatizing, but using different surfaces. And in cylindrical coordinates, you will use circles. So notice how I'm doing. These are circles. And it can keep going. So circles of different radius. The only parameter I'm changing here is the radius, right? Here I change the position of the surface. I need one more if I need to have a mesh, right? But now these are half lines. And what am I changing here? Angle, correct? So this is phi equal to phi naught. And here this is r is equal to r naught. And that's a coordinate. Is that clear? Right, so here what are the surfaces? A family of circles. So this is r is equal to r naught. And not really circles if you are in 3 dimensions, these are cylinders. Like this is a cross section of a cylinder. So r is equal to r naught, and because it's a cylinder, let me change the letter from r to rho. Right? So we'll keep the r for spherical coordinates. So this is surface cylinders, cylinder of fixed radius. Yeah, rho naught. Phi equal to phi naught. These are half planes. These are not full planes. Like here, these are full planes. This is a half plane in the sense that you start from the origin and go all the way to infinity. And half plane because phi equal to 0 and phi equal to pi are different sets of surfaces. So that's another surface. Those are half planes, which is described by a constant angle. And if you're doing 3 dimensions, you need another plane, and that will be a horizontal z is equal to z naught, which is the board itself. So z equal to z naught is a full plane. Of constant z naught. That's rectangular coordinates, that's cylindrical coordinates. What are the surfaces you will use to coordinatize spherical polar coordinates? Can you imagine? So we use these surfaces to pick a point, the intersection of these surfaces to pick a point in space. In spherical polar coordinates, what are the surfaces? So now we're doing spherical. So what are the surfaces you can think of? Intersection of 3 surfaces gives you a point, 3 planes here, 1 cylinder, half plane and a full plane. In a sphere, what do you expect? Let's start with the surface of a sphere. We talked about latitude and longitude, right? Let's begin with latitude. If you want to fix the latitude, that is 38 degrees, you said, right? 37 point something, 38 degrees. So give me every point on the surface of a sphere which is having 38 degrees. What will it look like?
Slice it with a point.
It will be a slice. So for example, so this is a surface of Earth. So that's every point on this surface, on this line, will be 38 degrees, correct? But we are in 3 dimensions, that's the surface of a sphere. If I extend this to another surface here, if there was a bigger Earth, how will that extend to? Give me a surface which has fixed latitude. If it was bigger, it will extend out. What will be the?
Oh, like a cone?
It will be a cone, right? Very good, right? It will be a cone. So you start from here. So this will be a cone.
Yeah.
Right. So that's your. So these are. This is theta is equal to theta naught, right? These are cones. Like as you change the angle, you change the cone. This is fixed radius. R is equal to R naught, and these are these are circles. Oh yeah, yeah. Welcome. Sorry. Oh, you're late, but that's okay. That's fine. You're late in the semester. Yeah. Okay. So R is equal to R naught, cone, and what is the third thing that is intersecting? What is the third thing you can imagine is intersecting? You need one more, or longitude, right? That's the way we see it. What is the surface corresponding to a longitude? So longitude will be like this. For example, if this is a North Pole. So now imagine this will be bigger and bigger and bigger. What is the surface that corresponds to the longitude of that?
Would it not just be a slice?
It will be a slice.
Like a plane?
Yeah,
What
plane.
slices it? defines that extends
So
out.
it's a plane, right? You're slicing it, but it's a special plane in the sense the back side of it is different because it makes a full circle. So it's a half. So probably that's what a slice.
Yeah, half plane.
So half plane. Is that clear? Right. So this will be half plane. So here is a quiz because you seem to have struggled to figure out what is this three surfaces. Draw a picture showing me just three surfaces intersecting to get me a point. Right? This is the point that we are talking about, right? Is that clear, the question? Show the three surfaces that intersect to give you a unique coordinate in space.
In
Three-dimensional space, in spherical polar coordinates. Okay. So this is cylindrical. Sometimes you also say cylindrical polar coordinates. And these are rectangular coordinates. These are the three primary ones, at least when you're a grad student. Those are the three ones you surely need. As a physics student, you should have this in your head up and any time you should be able to know this. Question?
Can you
Yes.
say the quiz question once?
Oh, quick question. In spherical polar coordinates, there are three surfaces that intersect to give you a unique point in space. Draw those surfaces and illustrate that intersection. And be creative. You have to draw these surfaces. Be creative. Yeah, it should be. I would expect that this is available on the internet. You should be able to see it. But yeah, at least it's not a very popular diagram that we see. Okay. Let's concentrate on cylindrical and rectangular. That means only two parameters are different. Z is equal to Z naught is the same. That's just for simplicity. Drawing is easier. That's the main idea. And if you have an origin here and there is a point, so that's a vector, correct? By a vector we mean this. But I want unit vectors down. We have I and j, of course. But how do I go about getting the equations for those unit vectors? That's the idea. And for that, first we say is that if you have one point here, that's a one coordinate, and very close to it, that's another point. I think I'll say A, this is R. And very close to it, let's say here, that's another vector, R plus dr. So a small change in the position, that's your dr. Right. R plus dr gives you R plus dr. And now we have already shown that a point in space, there are two ways of representing that. One is x comma y comma z, and another way is, these are the cylindrical polar coordinates, but let me in general make it very general, say that this is u1, u2, u3. And even though I write x, y, z, let me also say I'll also use x1, x2, x3. It is more common, even though we will differentiate between the two, it is more common to think of another set of variables, let's say x1, x2, and x3. I'll come to that in a minute, what that means, and also so that there will be a connection between these two, and this will be u1, u2, u3. It seems like I've brought in a lot of parameters at this point, but the main idea would be x is x1, so the upper
superscript will be x, this will be y, and this will be z. And in cylindrical polar coordinates, since we are already familiar with that, we will say rho is going to be u1, phi will be equal to u2, right? The cylindrical polar coordinates, rho the radius of the cylinder, phi and z, right? That's the u3. We already know the connection between the two. X is equal, so this is a diagram. Take a simple diagram. That's your x, that's your y, that's your angle phi, that's your rho, right? That's a right triangle. And you immediately already know that x is equal to rho cosine phi, y is equal to rho sine phi, and z is equal to z itself. Like, or z is equal to u3. If you want, it's u3, it's the same. Z is equal to z, let me write that. Rho, remember, is u1, phi is equal to u2, z is u3, and it can be also x3, z, and x1 and x2. So that's your notation. We want to make this generic, that's why I have used u1, u2, u3. But this is more familiar, so we want to keep this also. That's the main idea. Now, dr in, so we would like to write dr, that's your small differential element, that's this vector. Between two coordinates, any two coordinates, what's the distance between them? That's my dr, right? Not distance, this is a vector connecting them, right? Distance will be a number. So the vector connecting them is the dr. Once you have an infinitely tiny quantity, I can write it in other variables, and I would like to write that in terms of u1, u2, u3. We use chain rule. Right. So the r would be written as, use chain rule, this will be partial derivative of r with respect to u1 times du1 plus partial derivative of r with respect to u2 times du2 right. That's the idea of a partial derivative. Instead of doing it as one vector, you could use any other parameters. It's a function of three coordinates, so each one contributes to that. So that's the idea of partial derivative. Is that clear? We have used index notation. How will you write this in index notation?
Partial r with respect to ui dui.
Perfect, right? So you will first say that, oh, that's too much of work. So first I'll write this as a summation over I. So it is dr over dui times dui, where I running from 1 to 3 here. But then you say, I will have a notation that whenever the summation index comes twice, I will implicitly assume that that is a summation. So this is dr by dui and dui. Good. Right. That's our dr. So let me rewrite this. So dr is equal to partial derivative of r with respect to ui times ui. It's just starting with a simple idea that there is a differential vector, and I wrote that in a different coordinate system, and that will be given by the partial derivative idea. But here now this is a vector, right? I'll define this vector to be, so that's a definition I'm using now. This is I is equal to partial derivative of r respect to u of I. Okay. This is the change in that differential vector with respect to the first variable. Right? How much change do you make with respect to the first variable? If you want to look at it here, this is your first E1, that's your E2. In the differential element, those are all perpendicular to each other. And you're trying to write a general coordinate, that's your dr. Right? Instead of writing going this way, you write it as the sum of two quantities. Right? This, in our standard language of cylindrical polar coordinates, there are two unit vectors. There is a radial unit vector and an angular unit vector. This will be your radial unit vector. Right? That's what it will come out to. But for now, this is just a definition. But there are three of them. So this will be EI, EUI. Remember again, as a vector, we know this will be E1, EU1 plus E2, EU2 plus E3, EU3. Right? That's so. In a sense, we have defined our unit vectors that we use in a vector space by this E. Now we want to derive this for cylindrical coordinates. So we will do this. We'll start with R, and if you are starting from the scratch, you need some coordinates to begin with. So we will assume that all the ideas of rectangular coordinates are there. A sort of cheat in the sense that we are assuming that there is a vector to begin with, but it helps to get a feel for what is going on. So we'll assume that rectangular coordinates we are familiar with, but we will derive the cylindrical coordinate. But in principle, especially if you're doing general relativity, like we have no idea of the space around us, so we cannot assume anything. So that becomes more abstract. So here, we will assume that the idea of R is in rectangular coordinate is clear. So what that means is that, so x, so when I said x1, x2, x3, so that is also, help me. So yeah, I'm just going to write it. So this is R is equal to x in the I hat direction plus y in the j hat direction plus z in the k hat direction. So what's the cheat I have made? Is I hat, j hat and k hat, I'm assuming that we all have a clear idea of that. This also has to come out from this. Basically, I'm trying to build a basis vector, but I'm assuming that I hat, j hat and k hat exists there. So in that sense, it's a cheat, but it will help us because this is the first example. How you can do this is that if you don't want to have the cheat, is that assume rectangular coordinates, then go to cylindrical coordinates, and then go to the third one. Then you're not using the rectangular coordinates as your information at all. So then it is in between the two. So that's your x, y, z. And now E1 will be equal to E1 by definition is dr with respect to du1. But that was just a notation we used for rho. So let's come back to our now standard familiar notation. So that's dr by d rho. So that's d by d rho of x hat. So this is x I hat plus y j hat plus z k hat. Everywhere in space, the rectangular unit vectors are constants. They don't change with position. So they can come out of the derivative. So I have I hat times dx by d rho plus j hat. This doesn't always happen that they are independent of the position. So don't assume that to be always the case. Write x and y in terms of rho. X is, notice, rho cosine phi. Right? So if I take the derivative with rho, I get a cosine phi. Right? So this is equal. So remember, x is rho cosine phi. So and y is rho sine phi, and z is having no rho, right? So it's just z. So this is equal to I hat times cosine phi plus j hat times sine phi plus 0. So this is 0 in the k hat. What's the length of this vector? Is 1. Cosine square plus sine square is 1. So it's a unit vector. Even though I did not show it as a hat, you can understand that it's a unit vector. How does it look like, this vector? So this vector will look like, this is my I hat, that's my j hat, and if this is my vector, this is my angle phi, this will be like this, and the length of that is 1, right? X component is cosine, y component is sine phi. So that's your vector E1. If you think of this as on circles, that's basically your radial unit vector. This is nothing but rho hat. In cylindrical polar coordinates, we call that rho hat. So this is rho hat. So we have shown that E1 is rho hat, that's our familiar idea, but how did that come around? I started with an infinitely tiny vector, wrote that in terms of any 3 coordinates. I chose cylindrical coordinates. If you choose spherical coordinates, then you will get your spherical unit vectors, right? That's how you proceed, and that's your rho hat. So do the same thing with E2, right, very quickly. So that's dr by the second one, which is angle, right, phi. Right, so that's equal to d by d phi of x I hat, or x was, remember, rho, right? So this is rho cosine phi I hat plus rho sine phi j hat plus z k hat. Now we are differentiating with rho cushion, right? Now we are differentiating with rho. Cosine phi is sine, derivative of cosine is minus sine phi, so that's minus rho sine phi I hat plus rho cosine phi j hat plus 0 k. Is this a unit vector? It's not a unit vector. It's sine square cosine square. Its length is rho. So the basis vectors do not have to be unit vectors. Like when we write it in cylindrical coordinates, the way we write it, we always write it as unit vectors. But the way this is being derived, it doesn't. The EIs doesn't have to be unit vectors, right? So they are not coming out as a unit. But what is its direction anyway? This is, let's think of minus sine phi and cosine phi. That will be perpendicular to this. So this is, this direction we will call it phi hat. Okay. So that's, if this is angle phi, that's 90 minus phi, that's phi. Is that diagram clear? Is that visible? Right? Okay. So if you were to show this on a circle, this is your circle. This is your rho hat, and the tangent to that circle is your phi hat. It is actually perpendicular to the surface. You began with the surface, right? This was half plane. It is normal to that surface. Like it is the surface that you started with, and that is what decides that vector rho hat. That's your a phi hat, and in this way of writing, this is rho times phi hat. If I were to write it in terms of a unit vector that I am familiar with, then it is phi hat. But remember, if you're in a entirely new coordinate system, then you only get this, and you can call that whatever you want. But here, since it's a familiar vector, we said it is. Z hat will come out to be the same. E3 will come out to be Z hat itself. Right? That's Z hat. And so now we have 3 coordinates, or 3 basis vectors if you want, and we should be that should be sufficient. But for every 3 bases, and remember again, we haven't defined any distance here.
distance or the dot product has not been defined yet. So for every 3 basis vectors the way we define here, there will be another 3 basis vectors. So what are those? How do we get around that? So let's go back and let's go here. So let's find another set of basis vectors. This is E. Earlier I said this was E subscript I. This one I'm going to call E superscript I. So this is a covariant vector or covariant basis vector. Vectors, there are 3 of them. Right. Now I want to define what are called contravariant basis vectors, and that will be defined in the following ways. We have 3 coordinates, and those 3 coordinates correspond to surfaces. Remember again, cylindrical coordinates, these are cylinders, like you are having to specify a coordinate in space, cylinders, half lines, and then there is a full plane of z, right? 3 surfaces, we called them U1, U2, U3, right? And the gradient of that will be these new basis vectors for each of the surfaces. And what is the meaning of a gradient? If I have a surface and I calculate the gradient, what comes to your mind? Very good. If you have a surface, it's perpendicular to that. On this table, if I have to calculate the gradient of a function, what will be the or the function is this z plane. Sorry, this table being constant, that surface being a constant, easier surface. If I take the gradient of that, it will be normal to that. So gradient is normal to a surface. Gradient of a surface is normal to it. That's the idea of a gradient. So this is a normal vector. So normal, so that's the intuitive picture. Normal to ui is equal to a constant, right? The surface. Right? Normal means this is ui is equal to rho means circles. Normal to circles. U2 is equal to phi is a half plane, normal to the plane. U3 is equal to z is the surface, normal to z. So that's your intuition associated with that. But here we want to calculate this again. So E1 again, E1, this time upstairs, the contravariant vector. This will be equal to gradient of U1, which is rho, right? U1 is rho. This is again the cheat coming in here. The gradient operation, you have to be able to see this geometrically. But we have the luxury that we have rectangular coordinates for us. So we will work with the rectangular coordinates for this. But if you're in a brand new space, then you really don't have that luxury of the gradient operator having a visual feel for it. If you're doing general relativity, especially our space-time, 3 plus 1 dimension, we don't have a very good visual feel for the 3 plus 1 space-time. Then that's the challenge that comes about, that okay, what is the meaning of that gradient operator in that 3 plus 1 dimension, right? But here we are going to use that luxury, and this is equal to I hat d by dx plus j hat. So in that sense, that's a cheat. And rho. What's the derivative of rho? Rho, remember, is x squared plus y squared and then square root, right? That's the length of the vector here. Somewhere so the hypotenuse is x squared plus y squared. What's the derivative of rho with respect to x?
derivative of rho with respect to x, what will this be? Equal?
X over rho.
Very good. So this will be I hat times x over rho, right? Plus j hat y over rho, and this is z hat 0. There is no dependence in that. Is that clear? If I write this with rho in the denominator, you learn that I hat x plus j hat y divided by rho, that's the rho vector itself. That's a vector rho itself, that's a definition of the vector rho divided by rho, that's rho hat. Is that correct? So? Yeah, okay, that is a unit vector. Yeah. Okay. Good. Do the same thing with E2. This is equal to the gradient of the second surface. The second surface is half plane. Right? These are not full planes, these are half planes. Remember, angles, right? So this means gradient of a surface of equal angle. Phi has to be fixed, and then I take the gradient, and it will come normal to that. This is that surface. It will come normal to that. Visually, you know that it will be in this direction, right? That will be a phi hat. But let's calculate that. So this is I hat times d phi over dx plus j hat d phi over dy plus k hat d phi over dz. What is d phi over dx for a geometry like for this triangle? So if I'm doing d phi by dx, I have to get tangent, right? So tangent phi is y over x, and I have to calculate the derivative of this phi with respect to x. And so you have to take, so phi is equal to tan inverse of y over x, and you have to find out d phi by dx. You can start with tangent itself, so you can do this very quickly, and then I'll write it then. Right. So tangent phi is equal to y over x. Take a differentiate on both sides, and with respect to x, y is a constant. So secant square phi d phi is equal to minus y over x squared dx. Okay, that's differentiation with respect to x. I'll take this to the left, so I have d phi by dx is equal to minus y, which is rho sine phi. So this is rho squared cosine squared phi, and that is a 1 over secant square phi. Cosine square and secant square goes away, and you learn that this is equal to minus sine phi over rho. You can do the same thing for cosine, the derivative with y also, and what you get is minus I hat sine phi over rho plus j hat cosine phi over rho plus 0 k hat. And if you compare this with here, this is pretty much the same, but now the rho is in the denominator. This is actually phi hat, but not a unit vector. It has a rho in the denominator. And E3, if you were to calculate, this will come out to be C hat. Let me summarize this a bit before we proceed further. Well, erase this, you want to help me? Okay. So we have cylindrical polar coordinates, so they look like this.
So this is a element of, this is u2 is equal to a constant, and this is u1 is equal to constant. u1, u2, u3 is the three surfaces, and what we have defined is the downstairs first, the covariant vector, that has been defined as partial derivative of r with respect to ui. Notice a notation in index notation, when you have something in the denominator, when you want to have a symbolic convention on the left hand side, the denominator superscript becomes a subscript. Right? On the left hand side and right hand side, the indices has to match, but if one is in the denominator, that switches sign. Right? That's generally a notation that comes out. And so this is covariant, and contravariant is defined as gradient of r. No, gradient of u, right? Let me write that as, this is dui over dr, which is basically gradient of ui. You will see this notation more common when you're doing general relativity. You will see that all these two are related in a way, right? And the notation I have used is, which is not at all common, is to write the gradient operator in this form. It's not common because this seems to suggest that you're dividing out by a vector. Dividing by a vector is not defined at all. You never divide vectors. In that sense, it's misleading to write that, but it helps to show that connection in that. Okay. So that's what you have. You have two basis vectors. It turns out that they are very similar, right? Just to list them again, E1 is equal to rho hat, E2 is equal to rho times phi hat, and there is a z hat also. Let's write it right now. E3 is equal to z hat, and E1 is equal to rho hat, E2 is equal to phi hat over rho, and E3 is equal to z. Starting from almost nothing, we had a space, we coordinatized it. That means we figured out three surfaces that intersect to give you a unique point, and based on the coordinates of those three surfaces, we built a basis vector. From that basis vector, now we want to define what is a metric. Right? We already have a dot product available to us, in the sense that we are talking about A dotted with B. So we'll presume the standard dot product, that is our three-dimensional space, but we want to learn how does that look like in this new basis vector. So we have a measure already in that space. So based on this, we want to define what a metric is. So this will be defined as a metric. Metric is a way of measuring length. So what do I mean by that? So I want to find a distance. So the distance will be defined as the distance between 2 points. Right? Remember, if you have x1, y1 in a plane, and x2, y2 in a plane, what's the distance between them?
The square root of...
So distance square will be equal to x2 minus x1 whole square plus y2 minus y1 the whole square. If it is a really small distance, infinitely tiny, then that is the same as b square
is dr, if this is a vector, right, if this is dr, then you take a dot product between dr and dr. Right? The dot product of the vector gives you the length of the vector. Right? That's a definition of a vector. Vector multiplied by vector itself gives you the length of the vector. This is a vector which is difference between two coordinates. That's anyway a distance. So here the distance will be equal to distance squared will be equal to dr dotted with dr. But dr, we had a definition earlier in terms of u1. dr was, where was that? So dr was defined as partial derivative of r with respect to ui times dui, which is nothing but e of I times dui in terms of your vectors, right? Unit vectors. So that's equal to, let me write this as, so this is du I times ei. That is, I changed my positions of e and u. I'm pretending that this is all commuting, right? If you're doing quantum mechanics, or like more accurately, like if you're doing quantum gravity or something, that coordinates really don't commute, then you have to worry about these things. But here we are pretending that everything is classical. So this is Ej times duj. Why did I use a j? Because I cannot recycle indices double, right? I cannot double them. This is a dummy index. I cannot do it twice. So this is the same as this. That's clear. Whatever comes in here, this is what is called the matrix. I'm going to define this as Gij as Ei dotted with Ej. That will be my definition of the metric. And in the new coordinates, the distance is, so dr dotted with dr. This is a geometric object on the left side, the distance. On the right side, it becomes a coordinate dependent quantity. This is dui, uj, and this will be given in terms of 4 definitions, 4 quantities or 9 quantities, I and j. This is my definition of a metric, right? The dot product. So I have 1, 2, 3, 3 here, unit vectors. I have to find all the dot products. So dot product of this with this, this with this, this with this. So there are 9 dot products I can find. That's my metric. So let's calculate that. So just to get a feel for what it is. Any questions until now? So Gij will be 3 components, right? Let me write that down. So this is E1 dotted with E1, E2 dotted with E1, E3 dotted with E1, that is E1 dotted with E2, E2. So that's your 3 or 9 basically, sorry. That's your tensor if you want, the metric tensor. So this is called the metric tensor. Why is it a metric tensor? These are the 9 pieces that decide how you measure distances. This is a distance. It is dependent on 9 quantities. Those are your 9 quantities. But we can calculate this, E1 dotted with E2, that's all here, right? That's rho hat, rho hat. So that's your 1. Right? Rho hat times phi hat, you can explicitly do these things. So that's, let me write that here. So that's 1, 0, 0. And here, when I do E2 dotted with E2, I get a rho square. So this is 0, rho square, 0, this is 0, 0, 1. And just to remind you what this is, in spherical polar coordinates, if you're doing distances, you would say this is d rho square plus rho square d phi square plus dz square. Right? That's your scale factor. Right? In curvilinear coordinates, you will say that's a scale factor because a circle, arc length of a circle. So this is arc length of a circle. So if this was d phi, that length, right, is rho times d phi. That's a scale that you have to associate to measure the distance along an arc, right? So that shows up here. So these are called scale factors if you want. You immediately say that what if I use the other coordinates, right? So the metric tensor also can be, there's another metric tensor, there's Gij, which will be defined using the superscript or the contravariant vectors, that's Ei dotted with Ej. This comes out to be equal to 1, 0, 0, 0, 1 over rho square, 0, 0, 1. I can also define other quantities. This will be, in fact, it will always turn out, this is not very obvious, but it will always turn out so that Ei, if I were to do this with the other set, like if you were to mix up the contra and the covariant, this will always come to be an identity. They will always be orthogonal. So if you pick the orthogonal vectors, remember they were not normalized, right? Yeah, I shouldn't say orthogonal. They didn't come out normalized, right? The scale factors showed up. But if you were to mix them, one contravariant and one covariant, they will become normalized. So this will be 1, and I can do the opposite also. So this is often said as this is Ij. So in that sense, because it gets normalized by construction, you don't have to really normalize it. These are called dual spaces. So this is called the dual of each other. If you have done crystallography, if you're doing solid state physics, you will be seeing different vectors associated for crystals. There they are called reciprocal bases. One and the other, right? One of them is a basis, the other is a reciprocal basis. Exactly the same idea. You use it there, and there it is not curved, so you don't got to call it curvilinear coordinates. You only have simple vectors showing up there. And that's part of your, that shows up in your homework, but that's optional. This time the homework has 3 questions, but you don't have to do all the 3 questions. You have to do only one. But I'll encourage you to at least go over the problem so that you're familiar with what's going on. Okay, that's your GI, the metric tensor. This is orthogonality if you want. So given a basis vectors, there is a property called orthogonality or a normalization. And the way I have constructed them, they come up orthogonal if you mix the vectors, one from covariant and the other from contravariant. They are always orthogonal and normalized. Is that clear? Next, we want to say, okay, so if you have 2 vectors, I can always
put them together and multiply them as vectors. But there is also one more feature. We said if there is indices, I can add them, right? So let's find out what is EI and EI itself. Notice, see the difference between these two here. This is a vector, which I show it as a vector sign, and there are three vectors there, right? This, for example, here, there are three vectors. If I use index to show that vector also, so it's basically a tensor. I am taking a tensor and multiplying it with another tensor, but here I was using the vector notation to take the dot product, but now I'm using the index notation to take the dot product. This is a dot product also. I times I, remember, if you sum over the index notation, then it's a dot product. So this is also a dot product. This was 4 rank tensor, 2 of them gone, so there are still 2 vector nature depending on. Let's see what this is equal to. Since it's an index notation, this means this is E1, sorry, E1 up, right? E1 plus E2 plus E3. And that's equal to, in our case, E1, where, what is E1? No, one is up and one is down, right? So this is rho hat, plus E2, so this is rho hat, so 2 upstairs, so that's 1 over rho times phi hat times rho plus z hat times z hat. And rho cancels out. This is equal to rho hat plus phi hat plus z hat. And this might not be very familiar, but this will be always an identity vector. And why is that? There should be a more generic way of seeing this without being in cylindrical coordinate. But before I proceed there, this will be called the completeness relation. And it plays a very important role in quantum mechanics. In general, in any vector space, but we don't highlight it very much when we are doing, for example, calculations in electrodynamics. We don't use completeness relation so much, or at least we don't emphasize it. We do use it in many ways. So that's one. So why is that one all the time? We should be able to see that. So let's go back to this as a generic notation, right? So EI times EI, and not staying in the cylindrical coordinates. This is nothing but EI. Remember, this is here. That's your DUI over R. That was a gradient operation, correct? And the other one is R over DI. What is if there was DUI over dx times dy over dui, what is that equal to?
Partial y.
Very good, right? So this is a summation. This is nothing but dy over dx. Right? That's a partial chain rule. Right? So in that sense, this is nothing but d by dr of r. Two different vectors. So it's the change in the vector r with respect to a gradient, but this is nothing. If we bring back our notation,
that we have done before is gradient of r. What is that equal to? That's equal to 1, right? We showed that previously. That is 1. That's something that's very useful identity. So we are shown in any coordinate system, if you build these two unit vectors, one is a covariant unit vector, one is a contravariant unit vector, its geometry is that the contravariant unit vectors are perpendicular to the surfaces and the covariant unit vectors are a change. If you make the surface a small change, in what direction you make that, those two vectors will always come out to be a complete set of basis vectors. So, in summary is that we have two basis vectors, Ei and Ej, and then we have, so summary is we have completeness relation for any two contravariant and covariant vector, and that's Ei times Ei is equal to 1. So if you add up all these vectors, they will always be 1, and orthogonality is Ei dotted with Ej. You can say they are orthonormality conditions because they will always be equal to delta Ij, right? So summary is, find the coordinate, 3 sets of coordinates, find your covariant vectors, contravariant vectors, they will always satisfy this. This is all, I'm showing you how it works, but they will always have a completeness relation, they will always have an orthogonality relation. How do you use this? Now I have a vector, let's say. Now I don't, all this I was working in basis vectors, that is position vector, but now I say that I want to write something else in terms of these vectors, any new quantity in terms of this vector. Let us say that in terms of these 3 quantities, I have written a vector, a general vector A. I would like to write its components, right? A vector is represented in terms of its components. How do I define my components? So this is how you proceed. A vector A, you multiply it with 1 itself, right? 1 is, so this is a trivial statement, but nevertheless an important statement. When you do it again and again, if you are familiar with quantum mechanics, you will see that you will always multiply by 1 and then put a completeness relation. So that's what I'm going to do. So this is 1, but I'm going to use a completeness relation in there. So that's dotted with Ei times Ei. I multiplied it with a 1. 1 is nothing but completeness. Now I will use a parenthesis here. So this is the only, so this is more conceptual here, that I'm using a parenthesis here. It's pretty much, you don't even have to write that, right? To write a parenthesis, you don't have to write that, but that's conceptually, you're treating, you multiply that with a 1, and now I'm separating out a basis vector out of it. So 1 had a basis vector, I separated that out and define this as my components of the vector. So I have defined now Ai is equal to A dotted with I. That's how we understand our vectors. Nowadays, remember, if you have a diagram, that's exactly how you will say your vector is. That's your vector. Right? This is your I hat. That's your j hat. What's your component? It's a projection of A in the direction of I hat. This is the first component is the projection of A in the direction of E1 now. This is the components of A in terms of the covariant basis. I could have done the opposite. I would have been interested in what is its components in contravariant basis. You just do the opposite, right? You write it from the left hand side. this is equal to 1 multiplied with A. That's also perfectly fine. And then you will get is equal to EI times EI dotted with A. Define this to be I, and this is AI, and where AI is equal to I dotted with A. So now we have projections of a vector in a basis. Once you have such projections, now pretend that you have two basis vectors. One is cylindrical, one is spherical. And you would like to know how is one related to the other. And then what you would do is, there is another basis vector now, A. You can write that as A dotted with GI. GI, this is a new basis in the sense that it's a spherical part. And then you project them together, and that's part of your homework. Right? I take you step by step, and that's part of your homework, and they are called transformation vectors. In quantum mechanics, you transform from one basis to the other. This is the classical version of it, where you go from one basis to the other. They are called transformation functions. Okay. But I'll stop here, and that's part of your homework.